In this session, we are going to see a special type of binary search tree called AVL trees. So AVL tree is named after its inventors Adelson, Belsky and Landis, and it is named as AVL. It is also called as self-balancing binary search tree. And why are we going for this AVL trees? They have some control over the height of the binary search tree by letting it not to be skewed. So you should know what is a skewed binary search tree. So here is an example of left skewed binary tree and right skewed. So in left skewed, you will have children only in the left hand side, and in the right skew you will have children only in the right hand side. If this is the case, then all the operations, whether it is searching or insertion or deletion, all these operations will take more time. And to reduce that time complexity, we are balancing this binary search tree, and a balanced binary search tree will be called as a AVL tree. So the time taken for all the operations in a binary search tree of height h is always order of h. If height is h, then the time taken for operations will be order of h. So it can even be extended to order of n when it is skewed like this. So worst case, left skewed, right skewed. So when it is skewed like this, the worst case will be considered and the time complexity will be order of n. So when you are limiting the height to log n, then AVL tree imposes an upper bound on each operation to be order of log n, which is much lesser than order of n. So from order of n, we are reducing the complexity to order of log n. How? By limiting the height of the AVL tree to log n. How am I going to limit the height to log n? By making it balanced. It should not be left skewed or right skewed. It should be balanced. So by balancing, you can achieve this log n. So such a balanced binary search tree is your AVL tree. And here are some properties of AVL tree. As I already said, it should be a binary search tree. So all the properties of the binary search tree is applicable for AVL tree. So what are the properties of binary search tree? Left child should be always lesser than the root and the right should be always greater than the root. So the same property holds here also. Apart from that, you have a special feature called balancing factor to get a height balanced tree. So what is this balancing factor? It can be found by subtracting height of left subtree and height of right subtree. So height of left subtree minus height of right subtree will give you the balancing factor. And the permitted values for the balancing factors are -1, 0 and 1. Only these values are permitted for your balancing factor. If you are getting any other values apart from these three, then the tree is said to be unbalanced, and that is not an AVL tree. Okay, so here is an example. Let us start from the leaf node 2. 2 doesn't have any left or right, so 0 minus 0 will be 0. 10 doesn't have left or right, so height of left is 0, height of right is 0. So 0 minus 0 is 0. Coming to 3, height of left subtree is 1 and there is no tree in the right hand side. So 1 minus 0 is 1. Coming to 9, there is nothing in the left hand side and you have only one node in the right hand side. So height of right subtree is 1 and height of left subtree is 0. 0 minus 1 is minus 1. Coming to 6, the height of 6 is, here I have 1, 2. So 2, height of left subtree is having 2. And right subtree height is also 1, 2. So the balancing factor for node 6 is 2 minus 2, 0. So here, as I already said, minus 1, 0, 1 are permitted values, and all the balancing factors of all the nodes are within this permitted values. So it is an AVL tree. Let us take two more examples. Figure A. Here, let us see whether it is a AVL tree or not. First, let us check whether the condition for binary search tree holds or not. 3 is less than 6, fine. 2 is less than 3 and 6, fine. 9 is greater than 6, fine. 8 is greater than 6 and less than 9, fine. 10 is greater than 6, greater than 9, fine. So the properties of BST holds good. Next, let us check whether the balancing factors are satisfied. For 2, the balancing factor is 0. For 8, the balancing factor is 0. For 10, the balancing factor is 0. For 3, the balancing factor is 1 minus 0. So it is 1. For 9, the balancing factor is 1 minus 1. So 0. For 6, the balancing factor is 2 minus 2. That is also 0. So the balancing factor also holds. So figure A is a valid AVL tree. Coming to figure B. Is it balanced? No. Why? Balancing factor of 1 is 0. Balancing factor of 2 is 1. Balancing factor of 3 is 1, 2. 2 minus 0. 2 minus 0 is 2. So this is not a valid balancing factor. It doesn't hold. Therefore, this B is not a AVL tree. And here is an important point. The maximum possible number of nodes in an AVL tree of height h is given by 2 power h plus 1 minus 1. So make a note of this. This is very important. The maximum possible nodes. It can be lesser than that also, but the maximum possible nodes of a AVL tree of height h is given by 2 power h plus 1 minus 1. So you can search, you can insert, you can delete, all operations can be performed in your AVL tree as well. And the time complexity for all these operations are going to be just order of log n. Okay, let us move on to search operation in an AVL tree. The algorithm is, you have to get the search element, check whether the search element is there in the root node. If both are matched, then you have found the element to be searched. If it is not matched, then we need to check whether the element to be searched is lesser or greater than the root node. If it is lesser, then we will continue our search in the left subtree. If it is greater, then we will continue our search in the right subtree. The process is repeated again and again till we find an exact element. And if the element is not found, even after reaching the leaf node, we will come to a conclusion that the searching element is not there in the AVL tree. So here is a picture to depict how searching is performed. Let the element to be searched is 27 and we have a tree structure here. The root node is 21. 21 is compared with 27. 27 is greater than 21, therefore we are moving to the right. So if we move to the right, it is 28. Again 27 is compared with 28. It is lesser, so we are moving left. Again 25 is compared with 27. 27 is greater than 25, so we move to the right. Now we have found 27. So in 3 steps, just 3 steps, we got the solution. When we are following the concept of binary search tree and AVL. And a height balanced binary search tree is nothing but your AVL tree. See the property, all the left side values are lesser than the root and all the right side values are greater than the root. Similarly, all the left side of 14 are lesser than 14 and all the right side of 14 are greater than 14. So when this property is followed, is used, then the search operation can be successfully done in order of log n times. So the height of the tree here is 1, 2, 3. Even if you take in the right hand side, 1, 2, 3. So the longest path from the node to the leaf will be your height. Height of the entire tree means the longest path from the root to the leaf. So here it is 3. So that is how in 3 steps we got the answer. Assume that we are using a sorted array with all these elements in a sorted array. So how many steps does it take to identify, to search this 27? In 10th step only we were able to find the element. So that is the reason why we are moving for a tree rather than an array. Let us see how insertion and deletion are performed in an AVL tree. So either you are performing insertion or deletion, whatever may be the operation. After doing that operation, the balancing factor of every node has to be checked. So 2 scenarios are possible. If the balancing factor is either 0 or 1 or minus 1 even after inserting or deleting a node, then the AVL tree is balanced. But after insertion or deletion, when the balancing factor is not within this limit, is not 0 or 1 or minus 1, then the tree is not balanced. Imbalanced. In that case, to make it balance, we have to perform an operation called rotations. So rotation need to be performed to make it balanced. Actually, there are 2 types of rotation, single rotation and double rotation. In that single rotation, you have 2 subclasses. One is LL rotation, other one is RR rotation. So what is this LL rotation? When the imbalance is created due to the insertion of a new node in the right subtree of a right subtree, then the right hand side becomes heavy. See, 6 is here. I am inserting 8 to the right of 6. Again I am inserting 10 to the right of 8. Now check for the balancing factor. For node 10 it is 0. For node 8 it is 0 minus 1. So minus 1. For node 6 it is 0 minus 2. It is minus 2. The balancing factor is not 0, 1 and minus 1. A value minus 2 has come. So the tree is heavy in the right hand side. So to make it balanced, I have to rotate it to the left. This is called as left rotation. So to make it balanced, I have to rotate the imbalanced node to the left. Here the imbalanced node is 6. So that has to be rotated left. So assume that you are pulling this 6 to the left. So how will it be? After pulling it, 8 goes to the top and 6 comes to the left. So this is left rotation. Similarly, we have right rotation also. So when we have a right rotation, when the left hand side is heavy, you have to make it balanced so that you are pulling to the right. So the balancing factor of 1 is 0. Balancing factor of 2 is 1 minus 0. Balancing factor of 3 is 2 minus 0. It is 2. So here this node 3 is imbalanced. So the left hand side is heavy. So to make it balanced, you are rotating it to the right. So how will it be when we rotate 3 to the right? 2 comes to the top and 3 comes to the right. So now the tree is balanced and the property of BST is also satisfied. So this is how single rotation is performed. So here is another example. Assume this is a tree which is height balanced. AVL tree. Now if I want to insert 89, where will I insert? I'll start comparing with 45. 89 is greater than 45, so I will go to the right. 89 is greater than 63, so I will go to the right. 89 is greater than 72, so I have to insert a node to the right of 72. Fine, I have inserted. Now check for the balancing factor of every node. So this is 0, this is minus 1, this side is 1 minus 2, so it is minus 1. This one is 0, this one is 0. Coming to 45, to the left I have 1, to the right I have 1, 2, 3. So 1 minus 3 is minus 2. So it is unbalanced. So to make it unbalanced, I have to rotate. So here, where the node is imbalanced, here the node is imbalanced with a value of minus 2. We need to focus only on 3 nodes for this rotation. I repeat, very important concept. In rotation, that rotation has to be performed only among 3 nodes. So we have to carefully choose the 3 nodes. So after inserting this only, the tree has become imbalanced. So which 3 node has to be selected? Whether it is 89, 72, 63 or 72, 63, 45. So where it is imbalanced, this minus 2 is the place it is imbalanced. So we will leave this 89 and choose these 3 nodes to be rotated. So this is what, take only these 3 nodes. See, after taking these 3 nodes, you can infer that the right hand side is heavier. So what should I do? I should rotate left. Which one should be rotated left? 45 should be rotated left. So when 45 is rotated left, it will come to the left of 63. But there is already 54 to the left of 63. So don't worry about that. Directly you bring this 45 to the left of 63. So 45 comes to the left of 63, and now I have to place this 54 to the right of 45. Hope you can understand. Bring the 45 to the left of 63. Since already 54 is there to the left of 63, you bring that 54 to the right of 45 so that the property of BST also holds. So after this rotation, again you check for the balancing factors. So let us move on to double rotation. So in single rotation we have seen left and right. Now double rotation. So we are going to perform both left-right rotation and right-left rotation. So that is what is mentioned as LR. So assume we have CAB. I want to insert CAB. So C is a root, A is lesser than C, so to the left, B is greater than A, so to the right. So now you check for the balancing factor. For B it is 0, for A it is 1, for C it is height is 1, 2 minus 0. So 2 minus 0 is 2. So here it is imbalanced. So since we have inserted to the left and right, see, we have inserted here it is left, here it is right. Yes, so left and right. So what we have to do is, we have to rotate the parent left and the grandparent right. So both rotation has to be done. So let us see that with this example. See, first the parent is rotated left. After inserting this B only. So B's parent is A, grandparent is C. So parent is rotated left. So when I rotate A to the left, what will happen? B comes to the left of C and A comes to the left of B. I repeat, when I rotate A to the left, B comes to the left of C and A comes to the left of A, like this. Now it is the left side is heavier. So we need to rotate to the right. Yes. So which one will be rotated right? We have already seen the grandparent. So what is the grandparent? C. So C has to be rotated to the right. So when C is rotated right, B will come to the top, A to the left and C to the right. Now if you check for the balancing factor, it is 0 for all the nodes and the height is balanced. So I repeat, in LR rotation, see this is how the insertion will be. LR. So parent should be rotated left and grandparent should be rotated right. Parent of B and grandparent of B. Because after inserting B only, the tree becomes imbalanced. So in all these examples, you can understand that for rotation, we are concentrating only on 3 nodes. How big the tree might be. The focus should be only on 3 nodes. You have to correctly select the 3 nodes to be rotated. That is crucial. And I will give you a shortcut also. See, if it is a double rotation like this, you straight away bring this B to the root. And since C is greater than B, bring that C to the right. You will get this diagram. I repeat, in double rotation, whether it is LR or RL, the node at the bottom, we are focusing only on 3 nodes, right? The node at the bottom should come to the root. And then this root, if it is greater than B, it has to come to the right. If it is lesser than B, then it has to go to the left. In our case, C is greater than B, that is why it comes to the right. This is the shortcut. Coming to LR rotation, which is another type of double rotation. Here I have to insert ACB. So A will be the root. Since C is greater than C, to the right of A. B is lesser than C, so to the left of B. Now I have inserted into the right as well as left. And check for the balancing factor. It is 2 here because left hand side there is nothing, 0. And the right hand side you have 2. So 0 minus 2 is -2. So it is imbalanced. So what I have to do? I have to rotate parent right side, which is the parent C. I have to rotate the grandparent left side, which is the grandparent A. So first I am rotating parent to the left. Sorry, to the right. I'm sorry, to the right. So C is the parent. When I rotate this to the right, how will it be? B comes in the place of C and C comes to the right of B. Then I have to rotate the grandparent left, which is the grandparent A. So when I rotate it left, how will it be? B comes to the top and A comes to the right. So as I already said, use the shortcut method. The bottom will come to the top. Yes. And A, since it is lesser than B, it goes to the left. Now check for the balancing factor. For all the nodes it remains 0. So it is balanced. So hope you understand how single rotation and double rotation are performed, and the shortcut for this double rotation and selection of 3 nodes among all the existing nodes is crucial in rotation. You have to focus on just 3 nodes for this rotation. So let us construct a AVL tree with the following values. So the first step, 63. Node 63 is created. Obviously it is balanced. And then 9 has to be inserted. Since 9 is less than 63, it is inserted to the left. So find the balancing factor. For 9 it is 0. For 63 it is 1 minus 0. So 1. Next I need to insert 19. 19 is compared with 63. It is lesser. So it comes to the left. Already 9 is there. 19 is compared with 9. 19 is greater. Therefore to the right of 9. Now again you check for the balancing factor. For 19 it is 0. For 9 it is 0 minus 1. So it is minus 1. For 63, it is 2 minus 0. So it is 2. Now the tree is imbalanced. Why? Because 63 is having value 2. So here it is inserted in the left as well as right. So LR rotation, double rotation I have to perform. Focus is on 3 nodes. Focus is on 3 nodes. So we know the shortcut. What is as per the shortcut? 19 should come to the top, and since 63 is greater than 19, it will come to the right of 19. Yes? Yes. See, we got this after LR rotation. 19 goes to the top and 63 comes to the right of 19. Next, we need to insert 27 in this. 27 is greater than 19, therefore to the right. 27 is less than 63, therefore to the left. Again, you check for the balancing factors. It is as per the expected values, so no problem. Coming to insertion of 18, compared with 19 it is lesser, so compared with 9 it is greater, so to the right. Again you check for the balancing factors. It is perfect. Next, insertion of 108. 108 is greater than 19, so to the right. 108 is greater than 63, so to the right. After inserting, check for the balancing factors. It holds, therefore no problem. Insertion of 99. Greater than 19 to the right, greater than 19 to the right, less than greater than 63 to the right, lesser than 108, so to the left. So after inserting, check for the balancing factors for all the nodes. Since it is between 0, minus 1 and 1, it is perfect. Now insertion of 81. Greater than 19, so to the right, greater than 63 to the right, lesser than 108, so to the left, lesser than 99, so to the left. So here by inserting 81, three nodes have become imbalanced. Okay, so which 3 nodes should we select? Come from the inserted node, come from the place where you have inserted, and then you select the 3 nodes of which one node should have the balancing factor other than 0, minus 1 and 1. I repeat, you have to select 3 nodes. After inserting 81 only the imbalance has occurred. So select 3 nodes from where you have inserted, and there should be a node which is having a balancing factor other than 0, minus 1 and 1 among these 3 nodes that you have selected. So yes, these 3 nodes are selected because after inserting this one and this 3 node, one among the 3 node is having this balancing factor. So this consider this 3 nodes only. So it is heavier in the left. Therefore we have to rotate right. So when I rotate right, what will happen? This 108 will come to the right of 99. Yes, 108 comes to the right of 99. And now after rotating, again check for the balancing factors. It holds. So this is how AVL trees are constructed. So the same rule that you follow for BST also holds here, but after insertion or deletion, you need to check for the balancing factor of every node, and if it is not balanced, then you have to perform either single rotation or double rotation as per the requirement and make it balanced. Hope you are clear with the concept of AVL tree. Thanks for watching.